4:30. I don't see my face. It's actually a pleasant surprise. Oh, there I am. Hello, it's time to start. The recording started. I'm Victor Askin, and it's my pleasure and honor to introduce to you today's speaker, Professor Marina Gavrilova of the University of Calgary. You had her bio sketch. Her website is definitely worth visiting, at least to see how much somebody can achieve by a very young age. Professor Julia Taylor, hiding over there, and I attended a small but very pleasant conference on cognitive computing and cognitive informatics last July. And the best acquisition was meeting Dr. Gavrilova. On top of everything else, on top of her obvious credentials, we share an alma mater. She graduated from Moscow State University, the premier institution which manages to crawl its way into the top 100 universities in the world. I won't tell you how. She attended it like 150 years after me, but we are alumni of the same university. Professor Gavrilova.
Well, thank you very much, Professor Victor, for your introduction. It's really a true pleasure to be here today to share what I know and what I'm passionate about with all of you. And I think we share at least one common denominator, which is a passion and interest in information security. And my particular talk is related to two other very fascinating domains. One is biometric research that became very popular and very actively researched domain over the past 10 years. And second is machine intelligence and cognitive computing that I think are two of the areas that hold within itself path to more discoveries and more advancement that computer science can do in the coming decade. So with that, I would like to just briefly mention my background so you know a little bit more about me and what I do. I have co-created two laboratories about 10 years ago at the University of Calgary. One is Biometric Technologies Lab, which is one of the first biometric technologies laboratories in Canada and have links to a number of research institutions and labs across the world that do similar research. And another one is Sparks Laboratory on spatial information and visualization. I also co-created International Journal Transactions on Computational Sciences, which I have one copy here with you that I brought to Victor, and it will go to the library as well at Purdue University. And over the last 3 years, the past 7 years, I have written and co-authored 3 books, and they kind of go along with my evolving research. And the first one was on image pattern recognition, synthesis and analysis in biometrics. This is how our biometric laboratory was created with the CFI, Canadian Foundation for Innovation grant. The next one is my passion and my PhD training. It's training in theoretical computation geometry with applications to Voronoi diagrams. I'm going to talk about Voronoi diagrams very quickly. I will mention its fascinating data structure because it has application in number of domains, and the interesting things about it, just out of curiosity, for instance, if they looked at the pattern of the people walking in the crowd, apparently they walk along the Voronoi edges. If you look at the beehive or the patterns of the coloring of the giraffes, they create Voronoi cells. So they found in natures and constellations, and they found in molecular structures, in lipid bilayers, in some other chemical elements. They form the cells and the relationship between the atoms. So they exist in nature, and we know quite little about them. So this is the second book, and the third one just came out last year. It's about my most recent work in the area of security, biometric security, multimodal biometrics, and intelligence image processing for security systems. And once again, you can see the common theme combining intelligent image processing, security system, and biometric research. And here's just a number of events that I'm involved in, aside from ICCI Conference on Cognitive Sciences, where their conference on cyber worlds, and this year, in 2014, I will be organizing the very first biometric workshop as part of this conference. And there is a conference on Venn diagrams that I traditionally attend, and also international conference computation science, computation geometry, and application workshop that I run. So we talked with Victor about seminars that leave lasting impressions, seminars that just go very exciting but very quickly, and you don't remember what they are about. And this is a message that I want you to come out with today. And I really like it. It's by George Bernard Shaw. It says, "A reasonable man adapts himself to his environment. An unreasonable man persists in attempting to adapt his environment to suit himself. Therefore, all progress depends on unreasonable men." So I really hope as researchers, all of you unreasonable people. And this is what allows us to create and push the boundaries and do something that people did not think is possible 5 and 10 years ago.
And you will tell us about what happens to women also, right?
The man here, or the man, it's a great point and a great comment. From my perspective, I understand as a human being, a personality, a creative mind. Excellent. So my son, working on his presentation, defined his understanding of mathematical logic and showed me it just before I was flying to Purdue. So I thought, if my son, who's 16, can define mathematical logic by himself, I can at least attempt to define computer science. I have a little bit more rights. And essentially, there's been a number of definitions of computer science, and the concept evolved over the years. Since it was created, first it was just supplementary field to mathematics and something on the boundary between mathematics and physics. Then it was creating computer devices and designing the algorithms, definition of Donald Knuth, whom I had the privilege to invite as a keynote speaker to one of the events, but he unfortunately refused because he was definitely very, very old. But I communicated with him directly. So he's created as a study of algorithms. And I think that, and then it was a paradigm towards computational intelligence, but I think from my perspective, it's not merely study of algorithms, the efficiency, but a knowledge discovery empowered by new ways of thinking. And those new ways of thinking is really what pushes the boundary, what opens the door for us to create some new disciplines, some new sub-areas, subfields of the science, and to investigate even further. So I'm going to talk today a little bit about a couple of just new ideas. So essentially, it's a summary of where I think my research and my contribution to biometric research moves further from here, together with my colleague, Professor Roman Yampolsky. We are promoting a new research domains called artimetrics, artificial biometrics. In my biometric technologies lab, we work on developing new architectures, fuzzy multimodal, neural multimodal systems architectures. We would like to push forward a new paradigm, spatial temporal biometrics, social biometrics, context-based biometrics, multimodal cancelable biometrics, and cognitive biometrics that we kind of try to I drafted those words, and we try to move this forward with research in those areas. And then there are also new challenges, interrelative, physio-emotional, privacy, and predictability, heterogeneous systems. And all of this hampers our effects, as well as occasional cell phone calls, but that's okay. That's all right. Yeah, fully forgiven. Okay, so these are our challenges. So I wanted to start with the question, what is security? Each of you can pick your own definition. Wikipedia defines a state of being free from dangerous threat. It can be defined by safety of a state or organization against criminal activity. It's definitely an area of computer science and IT domain which has been on the rise. And also, some of us very concerned about privacy can say it's a concept only existing in theory and not achievable at all with the modern means of communication, regardless of you being connected or disconnected to the internet at the point. What is biometrics? Biometrics is a science which deals with automated recognition of individuals based on their biological and behavioral characteristics as traditionally been defined. Biometry is an area of mathematical statistical sciences and aspect of biology, looks at biological aspects of the human beings. And biometric system, essentially an automated pattern recognition system that can recognize, which involves verification, identification of the person by determining authenticity of a special biological and behavioral characteristic. So how does it all come together to the purpose of security? Aside from some of the previous discoveries, in Mark Twain's book, Life on the Mississippi, a murderer was identified by the use of fingerprint comparison. Sir Francis Galton, British anthropologist, who was also happened to be cousin of Charles Darwin, began his observation of fingerprints in 1880, and this is officially considered to be one of the starts of biometrics. But it was not up to around 1886, where French police detective and chief of police in Paris, Alphonse Bertillon, created his system of body measurements used on criminals, where aside from fingerprint, he also measured such elements as height, the weight, the symmetry and position of the eyes on the face, and you can see a sketch to the right of number of different measurements taken for each of the person. It was all categorized and stored in the database, obviously hand recorded at this time, and then it's created the rise to modern system of classifying using biometric information for identifying a person. So the unimodal system architecture will normally involve initial data, in this particular case in the eyes, being sensed and image obtained by the sensor module. Then there will be, after quick quality check, whether it's sufficient or not for recognition, we can go to the feature extraction. Then we can also enroll the data that we received in the system database. Matching module will compare the features or the original raw data to the data stored in the database, and then decision module will make identification or verification decision, which involves two things. Verification is one-to-one comparison. So essentially, we're gonna person enrolls in the database with the photographs and says and types his name in. The system will say, yes, this name corresponds to this picture in the database. This is an easy comparison. And identification one-to-many, the person comes in with his face without the database. It can be covert or overt observation of a person in the crowd. The photograph is taken, we want to identify what, who he is. Apparently, as you know, the Facebook came out this year with this technology to try to identify people based on their faces across the different pictures, looking at the environment, looking at their friends, and it's created quite a lot of controversy and discussions in the scientific world and the privacy and security conference, where I was invited as a keynote speaker in Victoria Tribute Privacy and Security Conference this year. There was a whole session devoted to discussion of this important subject and what application it has on lives of everybody. So in order to validate traditionally how well the system performs, there are a number of characteristics that been and criteria that's been created. For biometric systems, some of the common ones is going to be false accept rate, or FIR, a probability of imposter being accepted as a genuine individual, false reject rate, FRR, probability of genuine individual being rejected as an imposter. All of these are very well-known definitions in the biometric. They're most of the systems, commercial systems, or little databases, or the developments of the companies will be validated against. In addition to those two very important characteristics, we have RSA-SMC curve, receiver operating characteristics. Curve plots false acceptance rate against corresponding false rejection rate to understand the pattern or see the dynamics of the relationship. And CMC cumulative match characteristic curve shows the chance of correct identification within the top trend match result. So if we do have out of the database of 1 million, we have about 1% or 0.001% of the top matches, then this will tell us if we definitely are not going to find the correct person within this top match. And then we can analyze statistical data even further. We can look at genuine accept rate, fraction of genuine score exceeding the predefined threshold, and genuine reject rate, the fraction of pointer score below the predefined threshold, in order to validate how reliable our system is. So these are major characteristics and major factors that affect the performance of the system. Those characteristics really depends on the data that you're working with. And in Biometric Lab, we've worked with a variety of different types of biometric data. We've worked with initially physiological characteristics, physiological biometrics, such as fingerprint, face, ear, vein patterns, iris. Then we worked with behavioral biometrics such as voice and signature and the typing patterns and the gait. And as I will tell in the next slide, we're starting to work with newer biometrics that also came into the play. But for traditional biometrics that we're working with, the expectations are right now very, very high. Essentially, it's expected that the false accept rate will be below 0.1%, that the false rejection rate will be below 0.1%. They are not symmetrically not symmetric. They can differ based on the security settings, type of the biometric you use, or architecture that you use as well. And essentially, in order to achieve very, very high, above 99% accuracy of the performance of the overall system, we can use number of tricks and improvements, and some of those relate to the algorithm itself, some of those relate to the super powerful computers that we can use in parallel distributed processing, and some of those relate to the fairly new concept of multimodal biometric, or using more than a single source of information, and then performing decision making, combining information fusion using those different data inputs. And I'm going to talk a little bit about that as well. So in biometric image processing, it's one of the fields that links me to my background in PhD in computational geometry and image processing. We can perform the whole bunch of different operations, such as digitalization, compression, enhancement, segmentation, feature measurement, image representation, image model, and even design special methodologies. And there are tons of different methods that we can use. We can use filtering, smoothing, registration, hierarchical, morphological, or multidimensional models, deterministic, fuzzy, geometric, and statistical approaches to model and compare images, and classification, design, pattern analysis, and even machine learning in order to learn the patterns and compare them better. So all of those create fairly interesting individual projects. But where our overall research in my lab takes me right now is towards really the synergy of biometric and machine intelligence. So on the left right here, we can see physiological and behavioral biometrics as a two basic types of biometrics, biometric data that we can process, and we can apply supervised or unsupervised learning in order to learn and represent those models. We can use cognitive system architecture, fuzzy logic system architecture, multimodal system architecture in order to perform the match and make a conclusion about identification and verification. Where we can draw on more data and more factors is right here. So first of all, we have cyber worlds and virtual reality, which is representation of so-called alter ego of the person. It's a second nature, or it's part of the personal identity. And within these cyber worlds, we can try to identify through the avatars, the owners, through the owner avatars, and try to identify the behavior, normal, abnormal behavior, the patterns, and actors in this play. This given a rise of this little sub-area of research that we call artimetrics. Then we have social networks, and I call it big data. And the big data, under this big data, what I understand is everything which is collected about you, exists about you out there in the databases, in the customer surveys, in the workplace or in personal space, but not necessarily online. The first one, social networks, is all the social information that you have on Twitter, on Facebook, on blogs, on your uploaded pictures that you upload and share, and on the web. So, and this data provides vast materials for understanding even more about human nature, human communication, about ways to identify people, and about such phenomena as even Twitter or Wikipedia or Facebook, things that did not exist 20 years ago, but things that we increasingly rely on for our communication and information in the modern age. From there, from taking and studying all of this data, we can identify normal versus abnormal behavior, which can help with security concerns, patterns, whether it's been online or been when you physically cross a boundary or border of some countries. And in addition to traditional identification verification, we can perform additional special temporal analysis, which gives rise of a term that I call special temporal biometrics. We can have context-based biometric, which means a biometric that looks not only at something which is obvious, but auxiliary, supplementary information which can be found, such as time of day of the picture of taken, for instance, in the gate or the background where the person was walking for the gate recognition or surveillance video, or the typical behavior of the person, whether he's following the habit, whether he's not following the habits. And this can be used as part of either very serious security system, or it can be used to perform additional social and collaborative research. Even without all this complexity, we have enough misconceptions about biometrics, and those problems still remain up to now. There's so-called Hollywood perception of biometrics that is given to all of us. And for instance, it's for Hollywood face recognition, we can see a police guy in the helicopter trying to chase the car on the road with going 100, 150 miles per hour, and he managed to snap his picture from the right up there from the helicopter on the move, immediately identify, recognize the person in the database, tied into super database who knows who everyone is and makes no mistakes, and right after it, he is successful in finding vulnerability of this person or making an arrest. Obviously, this is science fiction. This is not what really happens, and there's tons of even tiny issues and problems that people can solve within this area, and it can keep them occupied for years and years of research. That's why the face recognition is still extremely actively researched domain in biometric, even after 20 years of very, very big successes in the field. Hollywood DNA has another misconception, assumes access to super database, has everyone's DNA automatically and rapidly processes a sample and makes no mistakes as well. So this shows you that even with the simplest individual biometric processing, there is still some challenges and issue. But what we're trying to look at globally, and what identified our current research at the Biometric Technologies Lab at the University of Calgary are the number of following research directions. So we're looking at intelligent image processing that I briefly outlined before. How do we identify the boundary? How do we perform image segmentation? How do we compare them? How do we deal with changes in illumination, in position, in rotation, the distance from the face? How do we deal with occlusions? How do we deal with process of aging? How do we deal with process of emotion recognition of the person, or how emotions change our perception of the person, or face recognition? So there's a whole bunch of issues rolled into one right here, and how getting the system to learn and to look at the patterns and understand the patterns and train the system on patterns can help to deal with those issues. The learning techniques that we're using, we were one of the first to use neural network for multimodal biometric system, and the research was published in Science Digest and a number of very good journals in addition to that. And we're looking at support vector machine, we're looking at topological and Werner-based clustering, evolutionary computing, cognitive system architecture, fuzzy logic as some of the techniques and approaches that can help us to design smarter and better systems. We also, aside from traditional types of biometrics, we also look at emerging biometrics such as infrared EEG, blood flow. We still investigate the problem of synthetic biometrics. It's an inverse biometric problem where instead of trying to identify person by biometric, we try to recreate the patterns of the person and learn from that. And then, as I mentioned before, there is a new research direction which we call social biometrics, web-based biometrics, spatial temporal biometrics, and cyber war security using biometrics, RT-metrics, that also allow us in combination to devise new ways to process this massive data and identify the person or the traits. Here's just a quick look at the settings in the Biometric Technology Laboratory. And right after that, I want to bring you back to the basics. This is one of the tools that we use to devise new clustering methods, published it in IEEE Robotics and Automation magazine a few years back. This was also a topic of invited research lecture at Microsoft Research that was also videotaped a few years back. So we're talking about Werner diagram and Delaunay triangulation, and right here on the left, we can see that it's defined as partitioning of the space onto polygonal regions, such a way that each distance from each side to any point within the region will be no further than from any other side. So essentially, the region around the Werner side determines the closest neighborhood of the points. We can imagine each of those sides, in this particular case, it's example of molecules, circles, but we can imagine each of the sides being, for instance, cellular or antenna on transmitting device. It can be bank that you try to locate, and you locate it anywhere within the space, and you need to find the nearest or the closest neighbor. And in order to find the closest neighbor in this particular case, regardless of where you located, for instance, you're located right here where my mouse shows, the closest neighbor will be one to which region you belong, so this will be the closest side. We use this in order to find the optimal path with specified clearance in the GIS system. We use it to find patterns in the and relationship in the data that we can collect. We can use it in order to build triangulation and look at clustering on the number of points, and we can use it to look at the molecular structure of the molecules, and all of this represent number of different applied domains where we use this methodology. In terms of I'm just gonna go back here. This resolution is not quite pulling off the video that I have right here, but essentially it's a dynamic algorithm that builds the clustering for the given set of points using Werner diagrams, and the outcome will be shown in a second with all these colors. So what we used it, initially is we used it in order to identify patterns in the fingerprints. We applied it to the fingerprint synthesis and fingerprint recognition analysis. And as it appeared to be the fingerprint structure, especially identifying the minutiae points, is very well represented by Delaunay triangulation, which is a dual to the Werner diagram. It's built in such a way that for every two Werner diagram sides, if there is an edge between them, they will be connected by the edge in the Delaunay triangulation. So it's a dual data structure to the Werner diagram. And what it allows us to do, it allows to introduce a number of very flexible measures For instance, we can model elastic deformations of the fingerprints very easily. We can model nonlinear deformations using the data structure. We can, when we compare the two of these data sets, we can compare regardless of the slight imprecisions in the angle and the distance and the area. So there's a number of parameters that allows us to compare the fingerprints using this particular approach, avoiding an error that some of the other methods do. And when we created this, we also got quite a large number of citations on this work using Warner diagram for fingerprint recognition. We got essentially the highest recognition rate for the fingerprint available this time. It's been used in a number of places, this particular method. So this is just a quick example of how the outcome looks. You have a fingerprint. There is the system will identify either that's but in this particular case it was a little movie done by National Film Foundation Canada, and talks about Warner diagrams and his history of research, and then how we research biometrics in this lab. Okay, a couple of other applications of the same approach to modern biometrics. We can use thermal images, for instance, for emotion recognition of the human, and emotion recognition provides huge hints on the state of the person, on whether he's calm or whether he's nervous. For the security applications, the emotion recognition in this particular case, and these images are provided by Pavlidis' report, it shows that if a person is nervous because he needs to lie, his blood flow rate will increase in the figure number D, and it will point out to abnormality or abnormal reaction to the question. In synthesis and analysis, biometric, here's a couple of more examples of synthesized iris that we create, synthetic fingerprints and synthetic online signature processing, as well as synthetic fingerprints. Now coming down to one more application of the neural network or machine intelligence for biometric. We can design a system that will learn from multiple traits. So it's going to learn based on face, topology of the face, and some additional feature vectors or even infrared information about the face. It's going to be, the information is going to be acquired for a number of different users. First, it's going to extract the features and create the feature set. Then it will choose and analyze the best set of feature vectors depending on the type of biometric you use. And then it will create chaotic associative memory with obtained vectors, train the neural network to recognize the common patterns. And once again, we're getting very high degree of precision of recognition using this approach to machine learning. Another direction that I mentioned before is using auxiliary or additional information, context-based information. And one of my master students did a successful research on using social context for gait recognition. So essentially, instead of trying to make the algorithm run faster or make it more sophisticated, we simply use additional information from the video. As you can see in this particular example, there's tons of information that can be obtained from here. We can see it's a day, we can see the person is walking outside, we can even identify the surrounding of the building behind the person walking. So all of this, in addition to the gait itself, which might not be perfect, increases significantly recognition rates. And so is in those particular examples. We also worry about security, and there's a fairly interesting concept that's been paid more and more attention recently. It's called cancelable biometrics. And cancelable biometric is a question that 5-10 years ago I was used to ask my graduate students, saying that what's going to happen if your biometric data has been stolen. If your passport is stolen, it's very unfortunate, but if you discover it, you can replace it. You can change the security system, settings on your system, and essentially you can deal with it. What happens if your fingerprint image is stolen? Somebody has your device and uses your fingerprint image. In fact, we run this as I believe Apple release a new iPhone, which uses fingerprint for login. The Discovery Channel Canada with Jay Ingram ran a recorded segment in our biometric technologies lab trying to break the security that is provided by using fingerprint. And in this particular segment, they managed to create a fake fingerprint using a jello and feed it to the device that simulates the fingerprint sensor, which is a commercial fingerprint sensor. And after the third attempt, it's got 80% or 70% match of the person and allowed intruder to get in. And it's literally took 10 minutes to create it. So with advancement of technology, at the same time with a huge imperfection of the technology, what can be done to mitigate those security threats? So we cannot change the biometric, but what we can do is we can use only fraction of the information available in the fingerprint when we create any kind of password which are biometric based. This allows us to extract the features, or we can mix up this information. We can apply encryption to this information. We can transform it, take it, convert it to another dimension, take it in another form. And this will allow us, even if the original will be compromised, to recreate another biometric-based password, because we're only using fraction of the information. So the key is never to store raw data in the full form, because in this particular case, if it gets compromised, there's no way to recover it. You're not going to cut off your hand or go to plastic surgery to change your face if that happens. But the key is really to use a number of security measures to protect it. So we're working in this domain as well. And then we did a number of very interesting applications to connect, identify virtual roommates using virtual biometric recognition, security recognition, and look at little bit futuristic, but nevertheless very, very real way of robot recognition, understanding. And under robots, we understand bots, we understand software, we understand virtual agents that exist in virtual spaces. We did a special issue in IEEE RAM magazine on robotics and biometrics, and there was large number of very high quality submissions in this domain from people working in both machine intelligence and robot authentication and navigation and artificial intelligence domains, because this is becoming another concern for security. So now, in the remaining 12 minutes, I'm going to talk in a little bit more depth about two last kind of fairly big areas and directions of our research. So one is multimodal biometric system. As you can see in this particular cartoon, the face recognition software will not be able to identify anybody in this company. They all look the same. So what can we do? Even if everybody looks exactly the same, or if the image of the face is poor, we can use another biometric such as voice or gait or gesture in order to identify a person. In fact, we just started a collaborative research with smart technology that allow us in the meeting room to identify and look at the contribution of the participant, at the body language, at the gestures that they make, to see who is a leading contributor, how people communicate to each other, how effective the meeting is run. And all of this can be picked up from those context-based auxiliary behavioral biometric traits and from combining those biometrics together. So here's an exact difference between single multimodal biometric systems. The single biometric system architecture shown to the right. We have feature extraction, feature matching, and get the final result. In multimodal, we have a number of different biometrics. The question becomes is what goes into this information fusion module. Before information fusion made its way about 7 years ago into biometric research, and we were some of the first to start working on it, and had a fairly well-cited paper in IEEE, transactions on system and cybernetics introducing multi-model rank-level fusion to the biometric research. This was very typically used in two domains. One is medical, and another is customer profiling and finance and banking. In medical domain, there's multiple symptoms, and one has to come up with a single diagnosis. And in customer profiling and banking, in retail domain, there's multiple factors that can play a significant part in understanding the ways how consumer works, whether he's going to become a customer, whether he's going to make a purchase. And those factors at the end was going to say you if this person is going to make the purchase or not, yes or no. And aside from that, there's some other domains where information fusion decision making is, of course, being used, but it's became very, very prominent direction of biometric research in the past 5 years. And right now, the number of different systems, multi-biometric systems, increased significantly. So the single biometric system faced numerous limitations that we discussed. The quality of the sample, orientation, rotation, distortion, noise, intra-class variability, non-universality, non-distinctness makes it sometimes hard for it to achieve very, very high results. This has been well accepted and well-known fact right now in biometric domain. And a number of advantages of multi-biometric system: A, they can offer substantial improvement in the matching accuracy. B, they can address the issue of non-universality on insufficient population coverage on one of the single biometric, on some of the data biometric traits by compensating using another's. And third, this final one makes life of imposter harder, so make it much harder to facilitate challenge response mechanism by when user or imposter tries to present random subset of different traits. So coming again to the same image, we can now solve this problem of people looking exactly identical. We can solve the problem that it makes it much harder for the intruder to break into the system because he needs to provide much more information to the system. And the final one, it also can be viewed as a fault-tolerant system. In this particular image is a real Intel surfboard that was created. And I guess the only thing, I mean, you can do anything. You can send an email, you can text, you can browse internet, upload yourself if you want to. But if you fall over the board, it's not becoming fault-tolerant anymore. You can't operate it. And so the multi-model system kind of gives you this cushion that even if you fail at one biometric, you're not going to fail at another. So now, going through this information fusion, coming back to this most important module, information fusion, how can it be done? So first of all, there's a whole bunch of different sources of multiple evidence. So we can have multi-sensor systems with different optical or solid sensors. We can have number of different algorithms we can apply to the same database. We can have multi-instance, right and left eye. We can have more samples for the, in this particular case, facial expressions. And then we can just have what most of the people understand as truly multimodal system, different types of biometrics. And it can be also combined in the hybrid systems. So there are various fusion level possibilities, and essentially this is a very interesting diagram because the levels of the data processing go left to right. So on the very left of this image, of this diagram, you will see that we have a raw data, then we have features extracted, then we have first decision, which is going to match initial images. So we're going to get match score or match rank obtained by the system, and the last one we simply have one decision, yes or no. So going from the left, from potentially it's a multi-dimensional data space, to the very right it's binary space, yes or no. We can apply different fusions at different levels. And the very first one is called sensor level fusion, the next one feature level, in the next one it's match or score length fusion, the last one decision level. The algorithms to make this decision become easier as we go to the right, but the precision also drops. So there is a fine balance And while the spectrum of those algorithms exists, most of the people work within either feature level fusion, image score rank level fusion, or even sometimes decision level fusion. And essentially, as we look at a little bit more complex structure now of multimodal biometric system, in this particular case, we have a enrollment. This is one of the first systems that we developed for face, ear, and iris process, and we have a system database which stores face, ear, and iris templates. Then we have started, after we extract the features, various types of rank level fusion, high strength border count, logistic regression, Markov chain, and we also introduced, aside from those Markov chain, we introduced the fuzzy fusion to the mix, and fuzzy fusion means that decision is not binary anymore. As a life, it's not just black or white. It has all the colors and shades of gray, and we're dealing and working now with all the colors and shades of gray, with the probability of sample being good, with probability of our decision being good, with probability of our algorithm being acceptable, that we can all measure and rank in the degree from 0 to 100. And when we combine it using special fuzzy system rules, we can get to different degrees of also confidence in our result, and this is what we call confidence-based biometric system, confidence-based fusion. And we can see that normally, once again, what our research showed, that using multimodal biometric system, if we're looking at RSA curve shown right here, any of those techniques, logistic regression, border count, high strength, will get much higher result. But if we combine it with some other techniques such as Markov chain, weighted majority voting, we're going to get even better results. I'm going to leave you with just a couple of pictures of our current research related to online security. So we have we can apply the same principles and the same ideas and techniques and methods of using machine intelligence, cognitive system design, fuzzy logic, multimodal system to online world as well. And in this particular case, we identifying industrial and personal robots, virtual world avatars, non-biological agents in the artimetrics and its extension of biometrics. We can use similar techniques on collection of robot data such as chat logs, synthetic voice recording, game strategy logs, etc., behavior, appearance, environment where those avatars existed. For avatar recognition, we use the same knowledge-based method, feature invariant approaches, template matching techniques, and hidden Markov model neural network SVM machines to learn about those methods. And we also can combine emotion recognition, which is going to be expressed itself through the chats, through the text, and through the visual patterns. And what we are going to go through next is gives the rise of the term which I called physio-emotional artimetrics. So together, behavioral physiological artimetrics in the virtual world can be utilized as part of physio-emotional artimetric system, which is yet to be developed. Finally, the very current research that we discussed with some of the members of the Purdue University security domain was on social biometrics, and we can create a social network using tweets. In this particular case, we have URL, reply, retweet, and hashtag networks, create a special network similarity threshold, and get the final similarity score, which allows us to compare how all of these emerging biometrics, such as Twitter biometric, can be used as a social biometric to identify people. Future research directions that we're moving on: social biometrics, using image processing for avatar recognition, behavioral context-based auxiliary biometrics, machine learning, cybersecurity, normal versus abnormal prediction patterns, cognitive methods biometric, and cancelable biometrics. And to learn more, you can send me email, you can Google me on the website, or go to Biometric Technologies Lab. There was a feature National Museum of Civilization in 2011-12 about Biometric Technology Lab. Science Daily and the BBC News and Discovery Channel did some features as well, and it's all linked through my website. So on that, I will stop my presentation. I think I used exactly 1 hour of my allowed time. So thank you.
2 minutes to spare.
2 minutes to spare, yes. I can spare 2 minutes. So I'm completely open for the questions right now and all that.
Questions, please.
Yeah.
Don't forget to talk into your mics.
And there's a lot to take in, but usually get tons of questions.
I remember maybe a good 10, 15 years ago, one of my scholars, PhD students, was working for benefits and he dealt with it. And I was told, maybe I misunderstood, that at that time, with the resolution that was available, no more than 300 types of fingerprints would be discerned. So I was shocked to hear,
yeah.
because that meant that there is 1 million people in this country.
There were
alone with
way
no
larger
fingerprints.
databases. Yeah, that is different right now. There are way larger databases. There's tons of different sensors that can acquire fingerprints using optic and ink-based, and even they can be acquired right now remotely, as you know, based on the temperature or the flow of the blood underneath the fingerprint, and based on the moisture that can be detected either by touching or remotely. So there's tons of technology went down from those devices 15 years ago costing over $1,000 to them costing $20. You know, we put them on the locks, on the displays, on the cell phones, and with the very high resolution, it's also the recognition rate went quite significantly up. So you can get it based on the fingerprint, considered to be one of the, first of all, very unique patterns. I believe I've been asked this question a number of times, but the siblings that look identically would have different fingerprints, so they can be even identified like that. And it's the recognition rate is definitely above 90%, maybe above 95% for most of the technologies. So this is considered to be somewhat a solved problem in the biometric domain right now. It's an individual task, but it's definitely, this is why it's one of the most acceptable technologies. It's used everywhere because it can identify you uniquely. So it's part of the biometric passwords for a number of countries.
How many different types are there?
Different types, there are 5 different types based on topology. There are also 3 different types of algorithms based on what we're looking for. We can look at minutiae identification, we can look at the ridges and valleys in the fingerprint, and then we can look at temperature and the other parameters, like physical parameters of the fingerprint, and pick it up. And in terms of there's even a model exists, which is the physics-based Newton attraction model that can model ears and fingerprints as well, based on the physical principle of particles being attracted to each other in these sizes. So it's been really well researched and been very, very successful. And face biometric almost gets to be as good at that. But this is if we talk about individual biometric, not the whole direction where the field is going. Any other questions or comments? Yeah, thanks.
How much of these change over age with any significance?
Yes, it's huge. It's one of the directions of research within the face recognition domain, and it has implications to customer profiling, updating the database of employers. It has implications for emotion recognition, reaction of the people to stress or to unusual environments, and obviously for the security, normal versus abnormal identification behavior in the lie detector test in stressful situations. So it has like all of those, a wide range of applications from social sciences to security domain, and it's considered to be unsolved problem. We can model how very well in animations and in Pixar studios. We can model beautifully how using non-realistic rendering or photorealistic rendering, we can model how people change, how they age, how they react to surrounding, how they express emotions. But when we need to recognize a person, the key is right now to have large number of samples, create very nice learning feature set that is independent of emotion expressed and use that to identify the person. But when we try to look for differences, not similarities, we're going to find that everybody expresses emotion in a very unique way. And there's a number of different theories exist that actually look at whether we can look at the muscle movements or we can look at the overall expression that the face transposes, or there's even research using EEG signals and the facial expression and effect of the smells and noise, the sound that you have on the behavior of the brain, and we can look at what happens in the brain when we have those expressions. So it's actually very interesting area. It's quite not well studied. Yes?
How do scientists working in this field approach the problem of privacy?
Yes, it's a fantastic question. So, there are a number of regulations that all of us scientists working in this particular field has to follow. For instance, you cannot collect or use any data without ethics approval being obtained. There are other things that you cannot do. So a number of studies are prohibited or not allowed or will never go ahead because of they being either controversial or too invasive to the privacy, etc. Unlike that, or at least understanding in the field that if there's a public data, it normally can be mined, it can be transposed, it can be studied, it can be taken, it can be researched. And companies do it, large companies do it, and organizations do it for their own purposes. And if something is essentially available publicly for anybody to see, it's not protected at the moment by any law to be studied, researched, and mined. As I was mentioning before, very quickly I've been to the Stanford University conference where one of the researchers just pulled out the public profile of two of his colleagues on the ResearchGate or available on LinkedIn or Google Scholar, and was talking about them because these are public profiles and you can analyze them and talk about it. It's not nice, but you cannot protect your privacy if it's public information. So if you want to keep something, and we discussed that European Commissions have much stricter rules and laws that will protect human privacy. For instance, you have a right to request to be removed from the database, request to be removed from certain listings, request to be removed from phone, companies' books there, and they have to oblige. If not, you can go and sue the company or employer, and we're still ways away from it here. But it's definitely, there's much more emphasis on it, and there are people working in this area.
At Purdue, as you probably know, there is the IRB, review board, and if you don't have permission for a very detailed proposal, you cannot do it.
Absolutely.
Okay, thank you very much.
Thank you again.